Hello, everyone. I'm Olympia. Thank you for being here with me in this wonderful place called Lights Out Library. And I have a great story to tell you. We are returning to space tonight. This journey is going to be our biggest ever. We are not just going to visit a particular planet or a part of the solar system. No, by the power of imagination, we're going to accelerate to several thousand times the speed of light. We will escape the solar system in a matter of seconds and travel to other galaxies. Along the way, I will tell you about our galaxy, the Milky Way. We will discuss other galaxies too, like our destination, Andromeda. I will explain the mind-blowing distances within and between galaxies, their populations of billions and billions of star systems, how the existence of galaxies was discovered and how they are observed. We will discuss mysteries like the possibility of life on these hundreds of billions of planets they contain, the possible existence of invisible dark matter in the universe, and how fast it is possible to travel in space. As usual, you don't need to worry about the complexity of all this. Everything is going to be easy to understand, even without knowledge of physics or astronomy. Everything will fall into place if you just let the sound of my voice guide you and to keep an open mind. But first, I would like to take a few seconds of your time to let you know that we have a Patreon page for those of you who wish to and can support this project. Get more of it and listen ad-free on your favorite podcast app. Patreon is a platform that allows you to contribute directly to our work financially. Our least expensive tier is $3 per month, but it doesn't mean you get less. We let people contribute what they wish to or they can, and everyone gets everything that is on our page. Because the world is a better place when the sun shines for everyone. If you join, you will gain access to various new features. For example, you will have the option to listen to all episodes with or without background sounds. You will have the ability to download all these audios and participate in selecting future topics, and also direct communication with us to give us your feedback. We also offer advanced releases and updates on upcoming episodes. There are several stories only available to our patrons, and we add new ones frequently. We have added a link to our Patreon page in the description of the episode. But before we begin, let's take a moment to prepare for our journey ahead. If you'd like, gently close your eyes and let your daily concerns drift away. Find a position that feels natural and cozy. Perhaps make small adjustments until you're perfectly comfortable. Now, draw in a deep breath, a nourishing one, and as you release it softly, notice how your body responds. Feel the warmth flowing from your shoulders down through your neck, melting away any tension. Let your facial muscles become soft, your jaw loose, your fingers naturally open, and your legs completely at ease. And as you settle into this peaceful state, my voice will be your gentle companion as we begin our exploration together. We will soon leave Earth and go further than any human has gone before. The Andromeda Galaxy, our destination, is extraordinarily far, and yet you probably have already seen it. On a moonless night, and from areas with limited light pollution, it is so large that it can be visible to the naked eye from our planet. It appears in the same area of the sky of the constellation of Andromeda, hence the name given to the galaxy. Even though it is way, way beyond the stars that form that constellation of Andromeda. Before we reach this galaxy, we're going to accelerate beyond imagination, even beyond what the law of physics, as we know them, probably allow. We will come back later to that. But first, let's take a look at where our planet is in our galaxy. We are used to thinking about the position of Earth relative to other bodies in the solar system, the Sun at the center of it, and then the other planets and bodies that orbit the Sun. But the Sun is just one star among hundreds of billions that also orbit around another center, the center of the Milky Way. The understanding that we are part of a much larger disk of stars is recent, only a century ago. The Milky Way is shaped like a gigantic flat disk. When bodies orbit around the center, they tend to align on the same plane. This is an effect of gravitational forces that keep them together. They tend to align on a plane. But star systems or galaxies are not perfectly flat. The Milky Way's disk is 1,000 light-years thick and is estimated to be 100,000 light-years wide in diameter. So it is about 100 times wider than it is thick, like the proportions of a CD-ROM. Sometimes in pictures, galaxies are represented with an oval shape, but this is because they are represented seen from the side with an inclination. If an observer looked at the Milky Way at the vertical of its center, the galaxy would look circular. All galaxies are not alike. On our way to Andromeda, we will soon reach a dwarf galaxy that may be in the process of being torn apart by the Milky Way. Some galaxies have only tens of millions of stars. Others have hundreds of billions, and their shapes vary too. Among large galaxies, there are three shapes that have been observed. The most frequent ones, like our own, are spiral galaxies. Their stars are organized on a disk, but they concentrate on arms originating from the center. And most spiral galaxies have a central concentration of stars known as the bulge. This is why the center appears more luminous. In the periphery, these spiral galaxies have a much fainter halo of stars. The arms appear more luminous because they contain a higher concentration of stars, often younger stars that shine brighter. It is believed that these stars are born from nebulae, which are giant clouds of gas and dust. Sometimes part of the nebulae collapse onto themselves after a shock wave hits them, and the gravitational forces lead to the accretion of this matter into a new star and eventually planets around it. The Milky Way contains various nebulae. They are the matrix of star systems. And when a star dies after billions of years because its fuel is exhausted, it may disintegrate and give back the matter it was made of to a nebula. The majority of spiral galaxies also have a bar-like structure that extends from the bulge. The Milky Way has one. Its spiral arms begin at the end of the bar. Not all galaxies are spiral shaped, though. Another type is elliptical galaxies. These ones have an ellipsoidal shape, which is like a sphere that has been slightly flattened. Seen from afar, they look like a smooth and nearly featureless halo of light, with more luminosity in the center where the more stars are concentrated. It was believed when these elliptical galaxies were discovered that they were younger and they could later evolve into spiral galaxies. But we now know that this is not the case. In fact, the stars they contain are, on average, much older than the stars found in spiral galaxies. And finally, there is a last shape, irregular galaxies, which are the ones with no distinct regular shape. These ones are chaotic in appearance. They have no bulge in the center, so they are like clouds of stars. Some irregular galaxies probably once were spiral or elliptical, and they were deformed by an external shock or gravitational force. Generally, these irregular galaxies are much smaller, about 1/10 of spiral galaxies, and this small size makes them more prone to crash and eventually be absorbed by larger galaxies. This typology of galaxies was started by an American astronomer called Edwin Hubble, the same Hubble whose name was given to the Hubble telescope. He is one of the most important astronomers of all time because he extended our understanding of the cosmos way beyond the limits of his time. He was active in the first half of the 20th century. His main findings include the discovery that clouds of dust or gas that were visible from the Earth and were thought to be nebulae were in fact galaxies beyond the Milky Way, and that the Milky Way was just one galaxy among many others. So he would start to map visible objects in the sky of the Earth and differentiate what was part of our galaxy and what was at the extragalactic distance. Together with the works of other astronomers, he also contributed to discovering that galaxies that were more distant from Earth tended to recede quicker. This is important because this is a clue that the universe is expanding, and it became one of the elements that backed the Big Bang Theory and made it go mainstream. Since its elaboration, the Big Bang Theory has been backed by various proofs of that kind that it accurately describes the history of the universe. So, where are we inside our spiral-shaped galaxy? The answer is midway between the center and the side. The radius of the Milky Way is 50,000 light years, and we are approximately 25,000 light years away from the center and 25,000 light years away from the edge. To exit the galaxy, we could either travel along the disk, and at light speed, it would take 25,000 years. Or for a shorter exit, we could travel following the perpendicular to the galaxy's plane. And that would be faster, but would still require several centuries at light speed. This gives us an idea of the size of our galaxy. We are disproportionately small and slow to even imagine reaching the edges of the Milky Way, let alone travel to another galaxy. Andromeda is 2.5 million years away from Earth. This means that what we see when we look at the sky and see Andromeda are rays of light that the galaxy emitted 2.5 million years ago. If it were to disappear entirely, we would be informed of it 2.5 million of our years after the fact. The fastest spaceships ever built travel at a small portion of light speed, way less than 1% of it. But even if we could reach light speed or close, traveling to other systems in our galaxy would remain a very long journey. The diameter of the Milky Way, you remember, is estimated at least 100,000 light years. And there are generally several light years between star systems. So reaching another galaxy would remain very implausible. But if we suppose technical limitations can be overcome, is it possible to move faster than light? Our understanding of physics implies that very probably not, at least not for human beings made of matter as we know it. According to the theory of relativity, when a body with a mass, a measurable quantity of matter, accelerates close to light speed, its mass precipitously increases and becomes infinite, and so does the energy required to move it. So this is impossible. The light, photons that travel at light speed have no mass, and this is how they can travel so fast without seeing their mass tending towards the infinite. The increase in mass when matter accelerates and comes close to light speed has been verified in particle accelerators. In a particle accelerator, particles like electrons are propelled to observe their properties when they accelerate or when they collide. In the 1960s, scientists observed that at some point when the electrons accelerated, they needed to provide them with more and more energy to make them keep accelerating. And even though electrons came close to light speed, they could never quite reach it because they got heavier and heavier. And it is obviously impossible to provide them with the infinite quantity of energy that could move their infinite mass. Our bodies and everything we build are made of the same matter that can be tested in particle accelerators. And they are subject to the same laws, the same limitations. So it looks impossible, or at least implausible, that a human being will ever travel at light speed. For now, this is not really a problem even for the fastest man-made vehicles, because they are way slower than light speed. For example, one of the fastest flying objects ever built is a space probe called New Horizons. This probe reached the limits of the star system a few years ago. It reached a speed of 16 kilometers per second, about 10 miles per second. 16 kilometers per second is already a speed that defies our imagination. For example, it puts Los Angeles at less than 5 minutes from New York City, and a complete journey around the Earth would take only 45 minutes. But this is still very slow in comparison with light speed. Light doesn't need 45 minutes to travel around the Earth. It needs just a bit more than 1/10 of a second. It travels almost 20,000 times faster than the New Horizons probe. But even assuming that we could build vehicles that are thousands of times faster, and we could come close to light speed, interstellar travel would remain very difficult, very long, and intergalactic travel still out of reach. Okay, so now if traveling in a straight line is impossible, maybe another option would be to use shortcuts. We figure out that the universe is a three-dimensional space because this is a perception that our senses and our minds have. We know since Einstein's theory of relativity that this perception is just one aspect, one way of seeing the universe, and probably a very incomplete, partial one. A few scientists and many sci-fi authors have considered the possibility that shortcuts in the structure of our universe, shortcuts in space-time, could be found or even created to almost instantly travel to another point in the universe in what would be some sort of teleportation. Theoretically, the theory of relativity allows the existence of structures called wormholes that would link disparate points in space-time, like tunnels, with two ends that would connect different points in space, different universes, or different points in time. But this is completely hypothetical, and no wormhole has ever been identified. However, science fiction quickly embraced the concept decades ago because it was a way to explain or justify very long distance travels in a short time and give stories a varnish of scientific credibility, which is why the concept of wormhole has become quite famous. Even though the existence of wormholes is far from certain, maybe one day a wormhole could be identified. After all, black holes also were a very hypothetical, theoretical kind of object for a long time before they were finally observed. Wormholes would be pre-existing structures, but maybe this type of tunnel could also be created and controlled by actively distorting space-time, which would allow a spacecraft to create its own shortcut to another point in the universe. This is also highly speculative, and there is no chance to see that kind of craft anytime soon, because we have no idea how to do that, or how to power such a spacecraft. At this point, we have no grip and no clue about how to actively modify space-time, if that's possible. But once again, science fiction is ahead, and that sort of modification of space-time to allow a ship to travel to other points in space or to another dimension is already familiar in fiction. Sometimes it includes a very cliché scene where someone folds a sheet of paper to show that any 2 points apparently distinct on a plane can be reunited, and the distance between them reduced to 0. This method of teleportation amounts to creating a man-made hole. But let's return to our journey for now. We are still not at cruise speed, but we already are traveling in imagination at hundreds of times light speed. We have left the solar system behind, and we are now in an interstellar void, on our way to the closest star system to Earth, Alpha Centauri. Alpha Centauri already gives us a glimpse of the diversity of stars and systems in our galaxy. At only 4 light years from Earth, it is not a single star system with planets orbiting around their star, like the solar system. It has 3 stars. 2 of them are rather similar to the Sun, and they orbit together around a common center, forming a binary star. From the Earth and to the naked eye, they look like one single star that appears in the constellation of Centaurus, hence the name of the system. But they are not alone. There is a third, less visible star that is almost invisible from Earth, Alpha Centauri c, or Proxima Centauri. This star is called a red dwarf. Red dwarfs are smaller and cooler than sun-like stars, which makes them harder to spot because they don't emit as much light. Red dwarfs are very abundant. It is estimated that they represent more than half the stars in the Milky Way, and they can also potentially exist for way longer than other types of stars, because when they burn their fuel, atoms of hydrogen merging together to create helium in the core of the star, the resulting helium is evacuated from the core by a convection movement. This means that the fusion reaction can last a long, long time. Red dwarfs are estimated to be able to burn for thousands of billions of years, as opposed to mere billions of years for more shiny stars. This lifespan represents much, much more than the average of the universe, estimated at about 14 billion years. So all red dwarfs are still very young, and none of them can exist at an advanced stage of evolution. Proxima Centauri orbits around the two other bigger stars. The system remains little known, but planets have been discovered in it, including one called Proxima Centauri b, that orbits around the red dwarf. This planet is the closest exoplanet to Earth that has been discovered until now. Exoplanets just means planets outside the solar system. I have a story on exoplanets in my library if you want to check it out later. This one, Proxima Centauri b, is in the so-called habitable region around its star. Habitable region means that, in theory, given the distance to the star, the planet could have conditions of temperature or radiation that could possibly be compatible with the existence of organic life on it. Now that we have reached Proxima Centauri, we're going to accelerate even further and travel thousands of light years in mere minutes to reach the edge of the Milky Way. As we start to see it from the outside, we may notice that the entire galaxy is spinning around its center. We will see later, when we arrive at Andromeda, what lies in the center of the galaxy. It may all look very slow because of the distance, but all star systems orbit around the center at high velocities. For example, the Sun and the Earth travel at 230 kilometers per second relative to the center of the Milky Way. This is about 143 miles per second. This is less than 1/1000th of light speed, but much faster than the speed of Earth relative to the Sun. The Sun's orbit around the center of the Milky Way is so large that it takes more than 200 million years to complete a revolution. This period of 225 to 250 million years is called the Galactic year, or cosmic year, and it represents entire eras for our planet. Even dinosaurs, if we accept birds did not exist for long enough to complete a galactic year. Humanity has been around for only a small fraction of a cosmic year. I told you earlier that Andromeda was the closest galaxy to the Milky Way, but this is actually disputed. It is the closest large spiral galaxy, but there are many other smaller galaxies in the proximity of the Milky Way. One of them is the Canis Major Dwarf Galaxy, or Canis Major Overdensity, because its status as a galaxy is unclear. This would be an irregular galaxy, located in the same part of the sky as the constellation Canis Major, seen from the Earth. This galaxy would contain about 1 billion stars, which is not much compared with the Milky Way that has at least 400 billion stars. This galaxy, or overdensity, would be in the process of being torn apart and absorbed by the Milky Way. Maybe Canis Major came too close to the Milky Way. In any case, it appears to be losing stars to the gravitational pull of our galaxy, and it forms a trail of stars around the Milky Way. But it isn't clear whether it is or was a distinct galaxy, or just a part of the Milky Way's halo of stars. In any case, an existing theory is that galaxies may grow in size over time by absorbing smaller neighbors. Now let's leave the Milky Way behind and accelerate again to reach Andromeda in a matter of minutes rather than millions of years. We are now in the intergalactic void, which is not very different in nature from the void between bodies inside a galaxy, except it is even more gigantic. It is as close as you can get to absolute vacuum. But there is not nothing at all. On average, estimates point to probably 1 atom of hydrogen per cubic meter. But in some regions of intergalactic space, there are more things. There are clouds of gas ripped away as galaxies interact or sometimes collide. It is difficult to study the intergalactic medium because visually it sends us close to nothing. Only light-emitting or light-reflecting objects like stars can be seen from Earth. Optical light is not very useful, but it is possible to study how light from galaxies that are further away travels through this medium and make hypotheses based on the information. For example, we know there are clouds of gas because some of the light gets absorbed as it travels through intergalactic space. But there is more than gas. The Hubble telescope has observed stars that are not part of a galaxy and exist between galaxies. They may have once belonged to a galaxy, but they were separated from it. These stars are called stellar outcasts or intergalactic stars. And they are not that rare, even though they represent a very small percentage of existing stars. Several hundreds of these free stars have been detected already in space between galaxies. Instead of orbiting around a galaxy center, these stars have been found orbiting around a cluster of galaxies, because galaxies are not the biggest unit in the universe. They tend to be located in groups where they are closer to one another in clusters, like the gas clouds I told you about before. These stars were probably ripped off the galaxy where they formed and belong to via the interaction or collision between galaxies. We don't know how many could be out there, but all the intergalactic stars detected were giants. There may be considerably more that are harder to identify, taking with them their satellites, their planets that accompany them on their lonely travel in space. If we look ahead now, we can see the spiral of Andromeda growing bigger every minute, with its arms spinning around the center. The observation of Andromeda and other galaxies is what has led to one of the most fascinating mysteries and hypotheses in astrophysics: the supposed existence of dark matter. So, what is this about? It all started in the 1930s. By then, the laws of gravitation that we think determine the movement of all bodies in the universe when they have a mass and how these bodies interact were already well understood. But a number of abnormalities were detected, in particular galaxies that seemed to travel faster than they should have, or not exactly in the right direction. This ghost force that seemed to drive the galaxies in the cosmos remained mysterious, and there were not enough observations made with the limited technical means of the time, so that this apparent abnormality was left unexplained for decades. But one hypothesis was elaborated by an astronomer called Fritz Zwicky to explain the speed of galaxies. To explain this, he attributed them more mass than was thought, a mass that would be invisible. By doing this, he managed to explain their motion, and he called this additional matter dark matter because it was invisible. But then there was no immediate follow-up to his work on this until the 1970s, and in particular until the works of another astronomer, Vera Rubin. She observed the movement of the stars spinning around the center of their galaxies and noted that stars that were far from the galactic center were moving way faster than they should. What the laws of gravitation tell us is that the speed of a body orbiting another object depends on the mass of the central object and the distance between them. This is why in the solar system, for example, planets that are closer to the sun travel faster than planets that are far away. Their speeds range from 44 kilometers per second for Mercury, the closest planet to the sun, to 5 kilometers per second for Neptune. Earth is in between, moving at 30 kilometers per second. Now, if we apply the same logic to a galaxy, the stars that are closer to the galactic center should travel way faster than stars that are far from it, close to the ends of the galaxy's arms, except they don't. Stars that are 10 times further away from the galactic center in a galaxy like Andromeda, for example, travel as fast as stars that are way closer to the center. This is unexplainable by gravitation force, except if there is actually more matter than thought. And in fact, she worked on the hypotheses that a cloud of invisible matter existed around the galaxies, which would explain how they move relative to one another, and also the motion of speed of the stars that belong to them. But the problem is, a lot of this invisible or dark matter is necessary to explain the movement of stars, for example, in the Milky Way. It would have to be close to 90% of the total mass of the galaxy. In other words, 90% of the matter contained in our own galaxy would be invisible and unknown. This is not easy to believe. And since Vera Rubin's hypothesis, one of the questions that keep astrophysicists busy is, what is this mysterious dark matter? There are three possible explanations here. The first explanation would be that dark matter is mainly objects that are known to us, but hard to detect because they emit very little light to us, like black holes, gas clouds, or red dwarfs. We know these bodies exist and some have been detected, but even assuming there would be many, many, many more, the sum of their masses remains far from sufficient to explain the effect of dark matter. Too much mass is missing. The second explanation would be that there are particles out there that we don't know of and have never observed because they would not interact with light. What could be these mysterious particles? We don't know. Despite attempts to detect or even fabricate them in particle accelerators, nothing has been found until now. The third and last explanation, but it is unsettling, would be that the equations of gravitation are incorrect, and that a new theory of gravitation or something entirely new to replace it has to be elaborated. Various puzzling observations have been made. For example, a galaxy called Dragonfly 44 would have to be made of 99% dark matter to explain its trajectory. Other galaxies would be almost entirely devoid of dark matter, meaning that the distribution of this matter would be extremely uneven, depending on the galaxies. But at this stage, astrophysicists have had to conclude that either close to 80% of matter in the universe is unknown and has not been observed yet, or that the laws of gravitation are not accurate and need to be revisited entirely. Maybe in the future an explanation to this mystery will emerge. But in the meantime, it reminds us of how little we know about the universe still. We are now in the immediate vicinity of Andromeda, which looks a lot like the Milky Way because it has a spiral shape, but it is larger. Its diameter is twice the diameter of our galaxy. However, the mass of Andromeda would be rather similar at about 1,000 billion times, 1 trillion times the mass of our Sun. Like the Milky Way, Andromeda has its own system of satellite galaxies. Canis Major was mentioned earlier for the Milky Way, even though it is disputed as a galaxy. But the Milky Way has more than 15 dwarf galaxies that are proven to be part of the same system, and Andromeda would have a similar number. Given their trajectories, the Milky Way and Andromeda are expected to collide in roughly 4.5 billion years, and their merger would form a giant elliptical galaxy. Andromeda would have formed 10 billion years ago. That would be 3 to 4 billion years after the Big Bang, and the galaxy would be the product of the collision of smaller galaxies. In its first billion years, Andromeda was probably very active, with a high rate of star formation. But over the past 2 billion years, it is thought that the formation of new stars throughout this galaxy has almost stopped, and the youngest stars in the galaxy would all come from the captures and mergers with its satellite galaxies. These captures leave what are called stellar streams, and these streams are the remains of dwarf galaxies that have been torn apart and stretched along their orbit. Now that we can see the Milky Way from afar, we could see these stellar streams that may not be aligned with the galaxy's plane. Like our galaxy, Andromeda has hundreds of billions of star systems and hundreds of billions of planets too. It is really in the 20th century that we have realized that the universe was much, much bigger than thought before, or at least that it contained more objects than thought. Because until the appearance of the Big Bang Theory, the universe was estimated to be infinite and eternal, which was a guess based on the very limited information physicists had available. Another breakthrough in the 20th century was that the understanding of organic life and the physical and chemical processes that led to its appearance. Even though everything is far from explained and science only answers the how of things, not the why they ultimately happen. This is a metaphysical question. However, it looks well possible that the same physical conditions that have led to the appearance of life on Earth, or other conditions maybe, could also exist in other parts of the universe. The laws of chemistry are the same on other bodies in space, and the molecules that can combine to create organic life are relatively abundant in the universe. So even though the probability that it happens on a particular planet or satellite is very low, when you multiply that low probability by hundreds of billions for the number of planets in a galaxy, and then again by billions more for the number of galaxies, you can quickly conclude that the existence of life in other parts of the universe is a near certainty. Maybe it could even exist or have existed close to us in the solar system, on the moons of Jupiter, or even on Mars in the past. We also know that the universe was already 10 billion years old when the first traces of life, the first unicellular organisms, appeared on Earth, and other planets formed billions of years before Earth. But if life can appear in multiple parts of the universe and evolve like it did for us into conscious beings that could travel away from their planet of origin or send information like radio waves, how is it that nothing has been detected yet and that they haven't found us? The apparent contradiction between the absence of signs of extraterrestrial civilizations and the high probability that they exist, may be more ancient than ours, is called the Fermi paradox, after a physicist called Enrico Fermi, who participated in a famous conversation about this. Arguably, it takes a long time to travel in the entire Milky Way, maybe millions of years at subluminal velocity. But millions of years is not much when the age of most stars and planets in the galaxy is several billion years. we should have found or detected probes, or at least signs of intelligent life that can travel faster, like radio waves. The question was raised by Fermi in this conversation in the 1950s, but even before him, it appeared in a manuscript by Russian scientist Konstantin Tsiolkovsky in the 1930s. Under the same terms, how is it possible that the near certainty of the existence of intelligent life is nowhere to be found? Tsiolkovsky proposed one of the numerous explanations to this apparent paradox, what is called the zoo hypothesis. This hypothesis speculates that extraterrestrial life intentionally refrains from contacting Earth and humans, either because they are not interested — what could we know about their motivations anyway? — or because they want to allow for natural evolution, avoiding contamination. But they could be observing us like visitors observe animals at a zoo. Another possible explanation, called the rare earth hypothesis, is that the set of circumstances that led to the appearance of life and then the evolution of biological complexity is very rare or even unique to Earth. This hypothesis argues that there are so many conditions required for Earth-like life that this phenomenon is indeed almost unique. It takes a planet in a habitable zone of a star system, a guardian against collisions by asteroids, in the case of the solar system, Jupiter, a large moon, a magnetosphere to be shielded from solar radiations, an atmosphere, and oceans. And yet another filter is the transition from unicellular life to more complex organisms, which on Earth took hundreds of millions of years and may be a very unlikely event. If we follow the rare Earth hypothesis, the absence of signs of life is logical. It is because there is none. Or maybe life is not so uncommon, but intelligent species are exceptional. Life on Earth has existed for about 4 billion years, but what we call intelligent life has been around for only 3 million years. Of course, we define intelligence based on our genus, Homo, because this is what we know. But arguably, human beings have been able to send radio waves and spacecrafts to space. No other species that we know of ever did that before for almost 4 billion years. So it tells us that even after the appearance of life, it may take billions of years before intelligence appears. In the case of Earth, 4 billion years is long enough in comparison with the universe, which is 14 billion years old. Maybe the appearance of an outward-looking species like ours is something really extraordinary. And life is maybe abundant in the universe, but intelligent life, able to exit its planet of origin, is something truly exceptional. And that would explain why no trace of extraterrestrial intelligence can be found. Yet another hypothesis, because there are many, is the water world hypothesis. It presumes that planets where life appears have a much smaller land mass than the Earth, or no land mass at all. For forms of life that will develop in water, it is not possible to use fire or develop hands. And even though intelligence is possible, this would limit their capacity to communicate and even more, send objects to space. Other explanations are gloomier. One is that it would be in the nature of intelligent life to destroy itself long before it can establish contact through wars, or maybe disasters provoked by technology, or maybe the existence of periodic extinction on all planets due to natural events prevents intelligent life from moving, traveling, or establishing contact. They go extinct before they have time to do so. If we accept that other intelligent civilizations exist, maybe they are just too far apart in space or in time. If only a few such civilizations appear in a particular galaxy, they may just not have had enough time to meet yet. Following the same logic, the beginning of radio emissions by human beings on Earth is very recent. The first radio wave emission was in late 1895. And even though radio waves propagate fast, they have only traveled a very small fraction of the Milky Way yet, reaching only a few hundred star systems at this point, when there are hundreds of billions. For example, extraterrestrials may transmit signals that have a very high or very low data rate, and they may employ frequencies we consider unconventional, which would make their transmission indistinguishable from background noise. Maybe another form of evolution for intelligent life, if it doesn't destroy itself, is that more advanced beings may strip themselves of physical form and transfer themselves to virtual environments that become their universe. They are no longer interested in exploring the physical universe we live in, and space exploration becomes meaningless to them. Or finally, it is possible that the perception that life is meant to expand and colonize is just a cultural feature of our species, born from our minds and the experience of life. Other civilizations may just have no interest in this and prefer to stay in their native world without even thinking about leaving it or exploring the rest of the universe. These are just some of the speculations that have been brought forward to explain the Fermi paradox. There are more. After all, some people also believe and suspect that aliens are already here. But let's take another look at Andromeda, especially its center. Like for the Milky Way, it has a bulge, a concentration of stars that look more luminous. Since the 1990s, the Hubble telescope has sent better and better images of this galactic nucleus. It contains millions of stars and a massive black hole at the very center. It is believed that galaxies, at least spiral and elliptical galaxies, have such a supermassive black hole at their center. And this is the densest part of every galaxy. Black holes are extraordinarily dense objects that pull other objects due to their gravitational force. We will explore black holes more in depth in a future story. One day, in more than 4 billion years, when Andromeda collides with our galaxy, the two nuclei may merge, or one will be torn apart. We don't know exactly how things will unfold. I'll take you on a new space journey tonight. But contrary to other journeys we made to other planets, stars, or even galaxies, the objects of our attention tonight will be much smaller. I'll tell you about asteroids, comets, and the phenomenon of shooting stars, meteors, when small asteroids and meteors enter and travel through our atmosphere. We have a lot to discover. Our cruise will begin in the upper layers of our atmosphere, and then, following the trail of these bodies, we will travel through the solar system, through the asteroid belt, and even beyond the orbit of Neptune. I will also tell you about different phenomena like how comets form, why and how bodies burn through our atmosphere, what a comet's tail is made of, and I'll also tell you about Oumuamua, this strange space object that was detected a few years ago and probably comes from another system. But before we begin, if you wish to, you may close your eyes and allow yourself to forget about any worries as we embark on this adventure together. Now, assume a comfortable position. Maybe move a bit to settle. Take a long, deep, relaxing breath, and when you slowly exhale, feel your shoulders drop. Release the tension in your neck. Let your face soften and your jaw relax. Make sure your fingers are not clenched and that your legs are relaxed too. And allow the sound of my voice to guide you through this journey. And now that we're all set, let's get started. Our cruise begins just a few miles above the surface of the Earth, above the clouds, a good place to observe shooting stars at night. You know what they are, a glowing streak of light that travels for a short time in our atmosphere and can sometimes be observed from the surface at night when meteorological conditions allow it. But shooting stars or falling stars are colloquial terms for a meteor. So what are the differences between these various words? Meteor, meteorite, meteoroid, asteroid, and comet. The differences are all about size, location, and composition. A meteor is synonymous with shooting stars. It is more a phenomenon than an object. The object that causes a meteor is a meteoroid, or an asteroid. The difference between a meteoroid and an asteroid is essentially the size and mass. A meteoroid is smaller, typically the size of a pebble. There is no official precise range of mass for meteoroids. But think about anything from the size of a grain of sand to a basketball. Meteorites are generally fragments of asteroids, which are bigger. A meteorite is what remains of a meteoroid or asteroid after it has fallen on Earth, if it has not entirely fragmented and burned. In summary, an asteroid can break into smaller meteoroids, and if they enter Earth's atmosphere, they generate meteors as they burn. Finally, if something is left of the body after impact with the Earth's surface, it will be a meteorite. A comet is a different type of asteroid. It has a particular composition, which we will examine later, and an orbit, a trajectory in space, that makes it periodically come close enough to the Sun for the interaction of solar radiation with its elements. This interaction generates a coma and a tail of gases and dust. which give the comet its well-known popular appearance. As we are now high in the atmosphere, let's take a look at meteors or shooting stars. They are the same thing. It is not that common to observe shooting stars, which might make us think that meteors entering the Earth's atmosphere are fairly rare. It is actually the opposite. It is estimated that about 25 million meteoroids enter our atmosphere each day. This is about 1 million each hour. Or, to put it another way, since you started listening to this story, about 100,000 meteoroids have arrived. But don't panic, because almost none of them can reach the surface. They are generally no bigger than grains of sand, and they turn to dust long before they could hit the ground. Only big meteoroids visibly catch fire and become meteors. The constant arrival of material that turns to dust and eventually falls to the surface represents a significant volume, about 15,000 tons annually. This means that the Earth gains about 40 tons of material each day due to meteoroids. 40 tons that end up spread more or less evenly as dust on its surface. Why do these meteoroids burn and break apart? As you know, it is due to the density of atmospheric gases. They are heated to incandescence. In the upper atmosphere, the density is sufficient to heat them to incandescence. This creates a streak of light when the object is large enough. It burns and sheds glowing incandescent material in its wake. Shooting stars typically look much closer than they really are. They seem to be a few thousand feet high in the sky, but in reality they essentially occur in the mesosphere, which is 76 to 100 kilometers above our heads. That's about 50 to 60 miles. As you also know, it is Earth's gravity that makes the meteorites fall toward its surface. Sometimes they can be space debris that was in orbit around the Earth and lost enough altitude to enter the atmosphere. But generally, meteors happen because of Earth's motion. As it travels on its orbit around the Sun, it crosses streams of debris, for example, left by a comet or that happened to cross its orbit. This is what causes meteor showers when suddenly plenty of large enough meteoroids enter the atmosphere together and become incandescent due to friction with air molecules. Friction, or, in the case of slightly bigger meteoroids, something called ram pressure, causes this heating. So what is ram pressure? When a body moves through a fluid medium like air, it compresses the medium in front of it, causing a drag force to be exerted on the body. In the case of atmospheric entry, it leads to strong heating of the air in front of it. This applies to meteoroids of a certain size, and even more to space capsules or space shuttles when they return to Earth. They were in the void or quasi-void, and suddenly they enter a denser medium with air around them. As they move fast, the air in front of them is suddenly compressed. A shock wave occurs, and this suddenly compressed air heats up due to the compression. This hot air will flow around the object and, in turn, heat it up to hundreds of degrees. It is this phenomenon that heats up meteoroids and makes them burn, rather than friction collisions with air molecules. However, it depends on their size. If their size is big enough, from 3 to 4 inches or 10 centimeters in diameter, ram pressure causes the majority of the heating. When they are smaller than that, friction is the main cause because they are too small to cause enough compression of air in front of them. A practical application of the understanding of ram pressure when objects enter the atmosphere is the design of space capsules or space shuttles. In the first years of space exploration, it was assumed that the best design for an object re-entering the atmosphere, returning to the Earth after a journey to space, would be one with a sharp, streamlined profile that would minimize friction and limit the rise in temperature. But a counterintuitive alternative was proposed: a large, blunt body concept. This is what you see in space capsules that return to Earth. They are shaped as cones. They are conical, and they present their base, which is wider, when they enter the atmosphere. This is because of ram pressure. It is taken into account that, given their size, the main contributor to heating as they fall towards the surface will be the compression of air in front of them. In other words, the transformation of their velocity, their kinetic energy, into heat, not friction with air, is the primary concern. So the question is how to optimize the evacuation of this hot air around the capsule with minimal physical interaction. This is where the conical shape is a good one. The hot air that flows around the capsule does not heat the walls much, only the base. Because the walls recede, they don't oppose much resistance to the air. To a lesser extent, the design of space shuttles is influenced by this. They have a large nose, not a pointed one. Of course, you still need a thermal shield made of material resistant to very high temperatures in the blunt base that will be in direct contact with compressed air. But this design turned out to be more efficient to facilitate re-entry into the atmosphere. Returning to meteoroids and asteroids that fall to Earth, as you know, they are sometimes big enough not to shed all their matter during their crossing of the atmosphere, and so sometimes they impact the surface. They can even be big enough to create an impact crater. Let's take a look at their composition, their size, and in some extreme cases in Earth's history, how their impact can have an effect on the planet as a whole. Meteorites, the remains of a meteoroid, are not that common. Normally about half a dozen to a dozen a year are observed to fall and are recovered for analysis. There are certainly many more that go unnoticed or fall into oceans, but a few dozen meteorites a year is almost nothing when you compare it to the millions of meteoroids that enter the atmosphere every day. Out of these few meteorites, even fewer are big enough to create an impact crater. Most of the time, they are no bigger than a pebble, and they create a small pit. But the possible crater and their size when they hit the surface is not only determined by their mass. A more important factor is what they are made of. Most of the time, impact craters on Earth are caused by metallic iron meteoroids. We will take a look at some of these craters in a minute. These are more resilient to the crossing of the atmosphere. Traditionally, three categories of meteorites have been distinguished. Iron meteorites are one of them. They are largely composed of metal, especially iron and nickel. Then there are rocky or stony meteorites. These are made of silicate minerals, which means that at the atomic level, they consist predominantly of silicon and oxygen. And there is a third category for composite meteorites called stony iron that contains a mix of metal and rock. Most known impact craters were caused by the first category, iron meteorites, because rocky material is easily disrupted in the atmosphere. This includes asteroids or small comets with a mass of several tons. They will break into smaller pieces due to heating and shock waves, and each of these pieces will be reduced to dust. Whereas iron meteorites are more solid, they will still lose much of their mass before impact, but some material may still remain intact. One hypothesis that has gained credibility in the past 10 years or so is that some of the complex organic compounds necessary for life on Earth could have arrived via falling meteorites. They would not have included complete living organisms, but rather large fragments of DNA and RNA that are fundamental to biological life as we know it. Why is this credible? First, because laboratory experiments under outer space conditions have shown that these compounds could form through chemical reactions on asteroids. Some very old meteorites, several billion years old, that we have found on Earth have also been found to contain liquid water. That was not a surprise. It is believed that much of the water we have on Earth arrived via massive asteroid bombardments when the planet was still forming. More interestingly, they also contain prebiotic organic substances, that is to say, some of the ingredients, the building blocks that make biological life possible. So while the idea that asteroids contributed to the emergence of life on Earth sounded like a long shot 2 or 3 decades ago, it is not as unlikely as it may sound. These compounds can form in space, and they can also resist entry into the atmosphere. As we have seen, there is a degree of molecular destruction when meteoroids crash and burn, but compounds may also be dispersed during the fall or preserved inside a meteorite. There are thousands of meteorites in circulation in labs, museums, and private collections, and most of them are fairly small. The largest known one is the Hoba meteorite, and it fell in Namibia, Africa. It is believed to have fallen sometime over the past 80,000 years. Its mass has been estimated to be more than 60 tons, and it contains about 84% iron. It now has a bit of rust on its surface due to oxidation. The fall of such a big asteroid on Earth would have caused significant damage theoretically, but maybe less than one could imagine in that particular case, because no big impact crater was found where it fell. An explanation could be the way it fell. These are just estimates, but due to its shape, it has been estimated that it slowed considerably during its fall. The entry speed into the atmosphere would have been typically in excess of 10 kilometers per second, about 22,000 miles per hour. But at the time of impact, it would have slowed down to just about 320 meters per second, 720 miles per hour. That is to say, below the sound of speed. This was still probably a violent impact, but at this speed and despite its mass, it would not have created a big excavation. This also probably explains why such a big meteorite could stay in one place. The most violent impacts in the planet's history, it is believed, saw the disintegration of the meteoroid or asteroid because they impacted at very high velocity and they disappeared. Their matter was scattered over a large perimeter and in the atmosphere. In recent history, a much bigger impact event is thought to be the Tunguska event, an explosion that remains somewhat mysterious that occurred in eastern Siberia in 1908. No impact crater was found, likely because the meteorite would have been stony and would have disintegrated at an altitude of 5 to 10 kilometers, 3 to 6 miles up in the air. That would still have been enough to generate a massive shock wave, which flattened the forest over an area of 800 square miles, destroying 80 million trees. In that case, the meteoroid would have been 50 to 60 meters in size, up to 200 feet. Because it happened only a bit more than a century ago, the Tunguska event is the largest recorded impact event in history. Much larger impacts happened in prehistoric times. The largest known impact crater on Earth is in South Africa. It is called the Rediscover crater and is estimated to be 2 billion years old. It is 100 miles wide, and it is believed the asteroid that hit must have been 10 to 15 kilometers, 6 to 9 meters in diameter. As is widely known, it is estimated that an asteroid impact caused, or at least contributed to, the extinction of most dinosaurs millions of years ago, at the end of the Cretaceous. This impact in South Africa is much older, 2 billion years old. Life on Earth would have been only ocean-bound, and the organisms were small. But an impact of that magnitude probably had catastrophic consequences on the whole planet because of the initial shock wave, and then the tremendous amount of dust thrown up into the atmosphere, changing the climate for months to years. It is expected that an object bigger than 1 kilometer across, 0.6 mile, could have global impact. And the one that fell at Rediscover crater was at least 10 times that diameter. The second largest known impact crater is the Chicxulub crater in Mexico and the Yucatan Peninsula. This one is much younger, 66 million years ago, and it is the prime suspect for the extinction of non-avian dinosaurs. That is to say, all dinosaurs minus birds, and also 75% of all species at the end of the Cretaceous period. At the time, the Yucatan Peninsula was under a shallow sea. It was not emerged like today. So now the crater is partially on land and partially underwater. But back then, the asteroid impacted the seabed. Contrary to 2 billion years ago, Earth at the end of the Cretaceous was teeming with terrestrial life. There were giant forests and all types of plants and animal species that were the ancestors of modern species. So the consequences on life, in the case of that impact, were probably much worse than the one that happened 2 billion years ago. First, because of the impact itself, which would have sent a splash of rock and debris into space, and upon their return to Earth, these flaming debris would have torched much of the planet. And then, because of a dust cloud that must have enveloped Earth for years, blocking sunlight, causing temperatures to drop and disrupting food chains. Now, this being said, should we worry about such a catastrophic event? Probably not. While it is still possible, statistically, the probability that it happens during our lives or our children's lives is close to zero. There are more serious pressing concerns to worry about. However destructive an asteroid impact can be, it could not really end life on Earth. Life is so diverse. It exists everywhere, including in the depths of the ocean, where it does not need sunlight. It could find a way to adapt and come back. Also, as the solar system ages, the quantity of large asteroid debris flying around on orbits that can cross ours has diminished significantly. All the very big impact craters are also very old. The youngest large impact crater on Earth, which is to say several miles in diameter, is in Tajikistan in Central Asia, and it is already 5 million years old. Now that we have looked at materials and meteorites that fall on Earth, let's leave our atmosphere and head to where they come from, or to the places where asteroids can be found. The official definition of an asteroid is that it is a minor planet of the inner solar system. They are called minor planets because the one difference with planets is their size. Asteroids are smaller. Obviously, there are smaller bodies outside of the solar system. Inner solar system means everything that is contained between the Sun and their asteroid belt, a large region of the solar system located between Mars and Jupiter. But beyond the last planet of the system, Neptune, there is another large belt, the Kuiper Belt, that contains millions of bodies that could also be called asteroids. The only difference with asteroids from the asteroid belt is their location. Let's take a look at the millions of bodies that float in the asteroid belt. Some are fairly big, but the majority range from a few inches to a few feet at most. The asteroid belt is located 2 to 4 astronomical units from the Sun. 1 astronomical unit is the distance from the Sun to Earth, so it is 2 to 4 times farther from the Sun than we are. It is where the majority of independent bodies of that size in the solar system concentrate. So why there instead of being scattered all around? The main hypotheses based on models of formation of the solar system is that these asteroids are the shattered remains of planetesimals, which are bodies that appeared when the Sun was forming by accreting matter. The dust that formed the disk in the early stages of the solar system. All planets of the system would be the product of this accretion. They absorbed all other bodies on or around their orbits through collisions and by attracting them due to gravitation. Actually, as we have seen earlier, this accretion process never ended completely. We talked about how Earth keeps gaining thousands of tons of matter every year due to meteoroids entering the atmosphere. But now the phenomenon is marginal in comparison with what it was billions of years ago. Some of these bodies were satellited by planets, but the majority were swallowed. However, not all planetesimals ended up becoming planets. Some were absorbed by bigger planetesimals, and others were ejected from the system, or at least from the outer solar system, by the gravitational influence of other planets, especially Jupiter. When Jupiter grew and neared its current mass, becoming by far the most massive planet of the system, its influence ejected over 99% of planetesimals in the belt. No planet or large enough body could form in this orbit between Mars and Jupiter. There were still collisions, but no body large enough to absorb the others ever formed. In this model, it is believed that many objects in the belt entered into orbital resonance with Jupiter. If you're curious about orbital resonance, I tell you more about this phenomenon in the story about Jupiter's moons. This would have been what led to their ejection from the inner solar system. Another model suggests that some of the asteroids that are now in the belt could have been captured from the outer asteroid belt beyond Neptune, the Kuiper belt, and dragged between Mars and Jupiter. So now there would be a mix of bodies, planetesimals that formed there that never became bigger than dwarf planets. For example, Ceres, the largest asteroid in the belt, was big enough to become round and differentiate. That is to say, the heavier elements it was made of, metal, migrated to its core, and lighter elements like rock or water became wrapped around the core. It is believed that Ceres formed in the asteroid belt, but this is not 100% certain. It could also have been one of these bodies attracted from the outer belt. Smaller asteroids would mostly be the remains of shattered planetesimals that did not collide with others to grow more. They stayed small or were shattered by collisions. In any case, we should not picture the asteroid belt as one of those asteroid fields that we sometimes see in sci-fi movies, where spaceships have to slalom between floating rocks. This kind of environment doesn't exist in the asteroid belt. To find something similar, we would have to go inside the rings of Saturn, for example, where there is enough density of floating rocks and ice. We could cross the asteroid belt without even noticing it because it is very empty. There are millions of asteroids, and about 1 million have been identified. They are much more common than in any other part of the inner solar system, but they are scattered over such a vast area that they can have millions of miles between them. Visually, the belt is not dense at all. About 1 to 2 million asteroids would be more than 1 kilometer large in diameter. That's 0.6 miles. And there would be millions more smaller than that. 200 asteroids are bigger than 100 kilometers. These ones have been named, and some of them have been explored by probes. Now, at the scale of the mass of the solar system, the asteroid belt is really not much. It's almost negligible. If we were to put all the asteroids together, we would get only 3% of the mass of the Moon. and one body alone, Ceres, accounts for 40% of the belt's mass. Ceres is the only body of the belt large enough to be round. The next ones are classified by mass, like Vesta or Pallas, are irregular because they are too small for their internal pressure to make their components melt, and they never took on a round shape. The surfaces of Vesta and Pallas show that they collided with other asteroids in the past, as evidenced by their craters. Although collisions can still happen in the asteroid belt today, they have become rare events. Because of the large distances between asteroids, collisions have become unlikely, and most of the time, except when involving Ceres or Vesta, they will not lead to accretion. These bodies are relatively small and don't have much gravitational pull, so instead they are more likely to shatter asteroids into smaller pieces. However, not all asteroids are located in the asteroid belt. There are other locations. First, there are asteroids called Trojans. They share their orbit with a larger planet or moon, but don't collide with it because they have reached points of equilibrium and stability that make them orbit always at the same distance ahead of or behind the larger body. Jupiter has many of these Trojans. Maybe more than 1 million larger than 1 kilometer are thought to exist in Jupiter's orbit. Unless a perturbation occurs due to another body, they will not collide with Jupiter because they always maintain the same distance. They are positioned in two groups, one ahead of and one behind Jupiter. Mars has 9 identified Trojans, and Earth has 2. The largest one is 1.2 kilometers, 3/4 of a mile, wide, and was discovered in 2020. The other one was discovered in 2010. These are both recent discoveries, and the second one is 300 meters, almost 1,000 feet in diameter. They are both hundreds of times more distant than the Moon. They could be less costly to reach in terms of energy because they are on the same orbit as our planet, by definition. They are small, but one day in the distant future, they could be a valuable source of rare elements that are technically present on Earth, but are very hard to access. For example, iridium, a very dense metallic element. There is iridium on Earth, but due to its density, it mostly sunk to the core of the planet shortly after its formation. These asteroids may have a similar composition to Earth, rock and metal, but since they are much smaller, it could be easier to access these rare elements on them. Beyond the asteroid belt and Trojans, there is also a smaller number of asteroids on orbits that pass close to planets. As of today, if we take Earth as an example, almost 30,000 near-Earth asteroids have been identified. These are the ones that are most observed for the possible hazard they represent. Their orbits are typically unstable because they are perturbed by Earth's orbit. Most of the time, this will result in their ejection from the solar system or a collision with the Sun, a planet, or another body. Of course, it is extremely unlikely that a collision will happen every time they complete an orbit. But given millions of years and millions of orbits, it will eventually happen. For that reason, these near-Earth asteroids survive in their orbit for just a few million years, There are still thousands of them because they keep arriving. It is believed that they generally come from the asteroid belt. The orbital resonance with Jupiter makes them migrate towards the inner solar system closer to the Sun, where they come nearer to the terrestrial planets like Mars, Earth, or Venus. A small number of near-Earth objects are also thought to be extinct comets that can no longer produce a tail because the elements that produce the tail have all been consumed. As we can see, there is a wide variety of asteroids, and contrary to the orbits of planets, they have remained fairly stable for billions of years. These asteroids are subject to various influences that can make them change position in and out of the solar system. These celestial bodies transit and travel, and we now know that they can move between star systems. Let's talk about Oumuamua, an object that attracted much attention in recent years because of its shape and origin. It is likely to be extrasolar. The shape is elongated like a cigar, and it measures between 100 and 1,000 meters, 300 to 3,000 feet. Oumuamua is a Hawaiian name because it was detected from an observatory in Hawaii. I mentioned earlier that objects, asteroids, may be expelled from the solar system. We discussed this when we spoke about the influence of Jupiter. But this does not make them disappear, of course. If they leave our system, they will travel in space, and eventually they can reach another star system, even though space within the galaxy like ours is mostly void. Star systems are very distant from one another. Typically, the distance has to be expressed in light years, but statistically, ejected objects will end up crossing the path of other systems that can include planets. We know that some planets are not bound, no longer bound to a star, and travel alone in space. Oumuamua is not very big compared to common asteroids in our system. We saw earlier that more than 1 million asteroids in the asteroid belt could be larger than 3,000 feet, and Oumuamua barely enters this category. But what revealed its origin is that it did not travel on a sun-bound orbit. It entered the system on a trajectory and with an initial velocity that prevented it from being captured. This meant that it would cross our system and then continue its journey. When it was first observed, it was only 0.2 astronomical units away from Earth. That's pretty close at the scale of the system, only 85 times as far away as the Moon. When it was spotted, it was already heading away from the Sun. Another thing that drew attention was that when it approached the Sun, it exhibited an acceleration that was not due to the Sun's gravitation. This was weird. It could have suggested that it produced its own thrust, but this wasn't unexplainable by natural phenomena. The Sun may have influence on other bodies beyond its gravitation. It can provoke outgassing, which we will discuss when we cover comets, or it can push things away due to radiation pressure. Of course, between the shape of Oumuamua, its extrasolar origin, and its trajectory and acceleration, it raised the question of possible alien technology. Could it be an interstellar ship? Though that would be a strange shape, and its surface appears red and similar to natural objects in the outer solar system. So it does look like a natural body, despite its unusual shape. a small number of astronomers suggested that Oumuamua could be a product of alien technology. They didn't definitely state this was the case, but noted that the phenomenon was unusual enough and difficult enough to explain to warrant attention. The majority believe that it is a natural object, and there are several hypotheses about how it formed. It could be a remnant of a disintegrated exoplanet, a comet from outside the solar system, or a piece of an exoplanet from beyond our solar system. But it is true that this particularly strange object will probably continue to draw attention in the coming years, as it is still inside the solar system. Now, let's talk about a particular type of body that is similar to asteroids, but with a few distinct characteristics: comets. As of today, there are more than 4,000 known comets in the solar system. Their most obvious difference from asteroids is that they can sometimes be seen from Earth with the naked eye, because they create a long, luminous tail in their wake. Why is that? How do comets work in general? The center, the nucleus of a comet, is hardly distinguishable from an asteroid. It is a loose collection of agglomerated ice, dust, and rock. The term ice here does not only refer to water ice like on Earth. In astronomy, ice is the term for compounds that are often found solid in space due to the low temperature, but that are volatile. They can be readily vaporized. It can be water, but astronomical ices also include carbon dioxide, nitrogen, ammonia, methane, sulfur dioxide, and others. All of this is contained inside the nucleus of a comet. Some comets are small and measure a few hundred meters across. Others are giant and measure tens of kilometers or miles. Like everything in the solar system, comets follow an orbit. But this orbit is highly elliptical and eccentric. Instead of revolving around the sun at almost always the same distance, like Earth, for example, Earth does not have a perfectly circular orbit. As you know, at some moments of the year, it comes slightly closer or slightly farther from the sun. But the difference in distance is comparatively very small, whereas comets can be 10 or 100 times farther from the sun when they reach their most eccentric point than when they are at their least eccentric point. We will see later that the type of orbits they have and the frequency of their returns near the sun depends a lot on where they come from. But the big specificity they have is that when they approach the sun following their orbit, solar radiation and the solar wind warm the ices they contain. Because they are volatile, they separate from the nucleus. They are released. This is the phenomenon called outgassing. These gases, water vapor, carbon dioxide, methane, also take dust with them and generate a kind of atmosphere around the nucleus. This atmosphere is called a coma, and it reflects enough sunlight to be visible from afar. This coma is not bound by gravitation to the nucleus because the nucleus is not massive enough for that. So it can visibly stretch behind the nucleus over long distances, up to 15 times the Earth's diameter. It would disappear quickly if it was not renewed by the continuing effect of the sun's proximity. These are basically volatile elements ejected from the comet's nucleus. The coma dusts appear when the comet has passed near the sun and starts to move away on its eccentric orbit. Once it is far enough for the ices to stop outgassing, the coma goes away, it disappears, and the nucleus returns to the appearance of a regular asteroid that will continue on its orbit and will stay without a coma for years, or up to hundreds of years, depending on how long it takes to return near the sun on the comet's particular orbit. But the most visible part of a comet that passes close to the sun is not this coma, actually. It is the tail. The tail is a second section of gas and dust from the nucleus that is blown out from the coma by the sun's light pressure and the solar wind. A stream of tiny particles that the sun constantly emits. The tail will typically be even longer and more visible than the coma. It can stretch beyond 1 astronomical unit, more than the Sun-Earth distance. The tail is typically what we picture comets with, as comets consume some of their matter to produce their coma, and their tail every time they pass near the sun. They have an expiration date. The nucleus will end up exhausted once it can no longer outgas, and it will keep revolving around the sun until it changes orbit, but as a comet asteroid, a dead comet. The solar system has existed for billions of years already, and yet there are still active comets. How is that possible? They should have died long ago. This is possible because there is a giant reservoir of potential comets beyond the orbit of Neptune, in the Kuiper Belt, and even more beyond it in a spherical cloud of icy bodies that extends beyond the Kuiper Belt, called the Oort cloud. It is believed that these potential comet nuclei can be seen in motion in the Kuiper Belt by the influence of planets, and in the Oort cloud by gravitational perturbations at the scale of the galaxy, for example, the passing of other stars. If their orbit is modified and brings them close enough to the sun to start outgassing, they become comets. So depending on where they originate, there are short-period comets that need a few decades to complete an orbit, and long-period comets that need much more time. The reservoir of comet-like bodies in the Oort cloud is estimated to be 1 trillion, 1,000 billion. This is why, with only a few thousand active comets at any given time, we will never exhaust this stock of potential objects. The solar system will disappear long before. The way comets work has been studied and quite well understood for decades. More recently, probes have visited them, which is quite an achievement given their speed and small size. A probe called Deep Impact, sent by NASA, blasted a crater on a comet called Tempel 1 and photographed it to study its interior. Another probe, Rosetta, sent by the European Space Agency, was the first to land on a comet and send information from there. Not all comets stay bound to the solar system. As I mentioned earlier, there are objects that can travel between stars. This happens if the trajectory of a new comet does not allow it to form an orbit around which it will keep traveling. These are called hyperbolic comets. After one passage near the Sun, they are ejected from the system and may or may not reach another system one day, where they will deploy their tail again if they come close enough to another star. Some of the most famous and expected comets include Halley's Comet. It is named after Edmund Halley, the publisher and friend of Isaac Newton. Using Newton's work, he realized that the comets sighted in 1531, 1607, and that reappeared in 1682 were in fact the same body, not three different bodies. Calculating its return and taking into account the perturbations the comet would sustain from the gravitation of the planets, he forecasted the comet would reappear in the sky in 1758. Indeed, it reappeared in December 1758. The comet has a period of 75 to 76 years. It varies slightly each time due to the effect of the more massive planets in the system, like Jupiter or Saturn. The last visible passage of Halley's Comet was in 1986, and it is expected to return by mid-2061. This comet was also the first to be observed in detail by spacecraft during its 1986 visit to the inner solar system. A lot of hypotheses about how comets work were validated thanks to these observations, especially the prediction that the comet's nucleus would be composed of a mix of rock, ice, and dust that we discussed before. Dirty Snowball was the name given to the hypotheses that comets were made of such elements, and it was outgassing that liberated the coma and the tail. When this comet is not in the inner solar system, it returns to the Kuiper Belt. It goes beyond the orbit of Neptune at a distance of 35 astronomical units, roughly the distance of Pluto from the Sun. It reaches its farthest point from the Sun. This point is called the aphelion, and then it starts coming back. Overall, it takes about 75 years to complete one orbit. Comets are classified as short period when their orbital period is under 200 years, so Halley is a short period comet. Above 200 years, there are long period comets. A famous example of a long period comet is Hale-Bopp, which became visible in the 1990s and was one of the brightest seen for decades. Hale-Bopp has an orbital period of 2,500 years, so needless to say, we won't be alive to see it again. Its aphelion, the farthest part from the Sun, is at 370 astronomical units. That's 10 times farther than Halley's Comet. It has a much longer orbit and comes from the Oort cloud. It stayed visible for 18 months in the 1990s, so we have plenty of photographs that show the coma and tail very well. As of 2022, Hale-Bopp has already crossed the orbits of Neptune and even Pluto's. It is traveling in the Kuiper Belt and will keep moving away from us for more than 1,000 years before beginning its travel back, after centuries spent in the silence and darkness of space, where the Sun is only a tiny point on the horizon. It took tens of thousands of years for mankind to understand the nature of the solar system, with a star and bodies orbiting around it. Then it took centuries to detect and name all the main planets in the solar system, and understand that the stars in the sky were countless other suns, parts of a galaxy. But it took only years to detect and name thousands of planets that do not belong to our system. Exoplanets. We're going to space again tonight for another cruise among the stars. And this time, I'm taking you to exoplanets, the billions and billions of planets that exist in our galaxy alone, which astronomers have started to discover rather recently. The identification of exoplanets is still a young discipline, so we're going to dream about those faraway worlds. We will spend our cruise traveling to some of them, like Proxima Centauri b, OTS 44, and Kepler 438b. And to entertain you along the way, I will tell you about the different types of planets and how we think they form, as well as the different types of stars, because not all stars are like the Sun. We'll explore how planets that are so far away can be discovered. Another big question raised by the evidence that so many planets exist in the universe is, could there be life on them? And what kind of life? This field of investigation, which studies the possibility of extraterrestrial life, is called astrobiology. And we'll talk about it too. So that gives us a lot to discover tonight. But don't worry about the apparent complexity of all this. Even if you have no knowledge of physics and astronomy, it's all going to be easy to understand with examples taken from daily life that will make these concepts sound familiar to you. If you like this type of exploration journey in space, there are various others available on my channel, like those in the solar system. But before we begin, if you wish to, you may close your eyes and allow yourself to forget about any worries as we embark on this adventure together. Now assume a comfortable position. Maybe move a little bit to settle. Take a long, deep, relaxing breath, and when you slowly exhale, feel your shoulders drop. Release the tension in your neck. Let your face soften and your jaw relax. Make sure your fingers are not clenched and that your legs are relaxed too. And allow the sound of my voice to guide you through this journey. And now, let's begin our journey among the stars. It took only a few years since the 1990s to discover and name hundreds of exoplanets, planets that do not belong to our solar system. Knowledge in astronomy has advanced much faster than our ability to travel in space. And these new planets are so far away from us that the hope of seeing human beings reach them one day is tenuous. But tonight, by the power of imagination, we are going to travel much faster than light and cross light years in seconds to reach our destination. Of course, everything we will visualize tonight is hypothetical. It is based on observation, deduction, and the state of our scientific knowledge. It is likely that the way we understand other systems and exoplanets will keep evolving. But still, there have been so many discoveries and so much progress in this field in the past 30 years that it has become a major aspect of modern astronomy. Our first stop on this journey will be at the nearest exoplanet that we know of, Proxima Centauri b, 4.2 light-years away from Earth. But how is it possible to detect planets that are so far away? The last big planet in the solar system, Neptune, was discovered in the 19th century. Then there was Pluto in 1930, which has been reclassified as a dwarf planet. But these are only a few hours' light away from us. Proxima Centauri b is hundreds of times farther, and no conventional telescope can actually take a picture of it. So, as we begin to accelerate, we are already leaving the solar system, and we will arrive at Proxima Centauri in a few minutes. Let's take a look at how exoplanets can be discovered. Any planet orbiting around a star is a very faint light source compared to its parent star. For example, in the solar system, the Sun is 1 billion times as bright as any of the planets that orbit around it. When you watch from several light years away, the light from planets is barely existent and gets completely washed out by the star they're attached to. So very few exoplanets have actually been observed directly, and astronomers resort to indirect methods to discover them. The first method is called transit photometry. What does it mean? Seen from Earth, other stars in our segment of the galaxy have a relatively stable brightness. It can increase or decrease with their distance to us because of all the planetary systems moving, orbiting the center of the galaxy at different speeds. But this is predictable. However, if there are planets orbiting these stars, these planets may regularly cross between the star and us. And this transit will hide a little bit of the star's light, not much of it, and it depends on the size of the planet and its distance to the star. But with instruments that are precise enough that a little variation in brightness can be detected during the planet's transit in front of its star. Sometimes the star dims significantly. There are examples with big exoplanets that make the visual brightness drop almost 2%. Most of the time, it is much less than that. For example, a planet the size of Earth transiting in front of a star the size of the Sun produces a dimming of only 0.01%. This is tiny, but still predictable with the right instruments. This method is complicated because there are many variables. The star may have several planets. It requires making assumptions about the characteristics of the planet's orbit. The dimming of light during transit is so small that errors, false positives, or transits that are not observed are probably frequent. It also requires the planet's orbit to be aligned in the right plane from the astronomer's vantage point. From where we are, there are planets that will never transit just in the right line of sight of their star. So it works, but only a minority of planets can be detected this way, and the larger their orbit, the less likely they are to be found. A second method that sounds very complicated, but the concept is not, is the use of radial velocity and Doppler spectroscopy. So what is this about? You know that planets are attached to a star by gravitation. This force keeps them in orbit around the star because the star is way more massive than them. But gravitation works both ways. The star has a major influence on the planet's orbits. And given that the planets are also massive objects, they have an influence, much smaller, on the star too. The bigger the planet and the closer it is, the more influence it has on its star. This means that the center of mass in a star system is not the exact center of the star. This center of mass is generally inside the star, but it's not the exact center of it because of the influence of planets. We generally say that planets orbit around the star, and this makes sense because the star in a system represents the bulk of matter, typically around 99% of it. Technically, planets and the star itself orbit around the center of mass, which happens to be inside the star if it's big enough. But a little bit uncentered. This means that the star also has a little orbit. It moves around a gravitational center. For example, in the solar system, Jupiter makes the Sun move by 13 meters per second. Earth also has a little influence on the Sun. It is much smaller than Jupiter due to Earth's smaller mass, but it influences the Sun by about 9 centimeters, a bit more than 3 inches per second. This is the concept of radial velocity, and these little interferences of the planets on their star can be detected. How? Thanks to a phenomenon called the Doppler effect. Light has the properties of a wave, and when you receive a wave emitted by a moving object, waves arrived a little bit distorted. Let's take the example of the Doppler effect with sound waves that we experience every day. You may have noticed that when an ambulance with a siren passes near you in the street, the sound of the siren changes quite a lot. When the ambulance is advancing towards you, the sound is higher pitched. Then it passes just near you, and the sound becomes lower pitched as it moves away. The same happens when you are near a railroad. The sound of the train changes a lot depending on whether the train comes towards you or moves away. This is not due to a variation in the sound from the siren or the train, and someone on board the ambulance would not perceive a different kind of sound. This is because sound waves are emitted by an object that is in motion relative to you. Try to imagine the waves as an undulating line. The waves from the siren are coming toward you, but so is the vehicle, and this tends to compress the line. It fluctuates faster. In other words, the frequency increases, and this makes the sound seem higher pitched. Now, when the vehicle moves away, the waves are more distant. The frequency decreases, and they sound deeper. This modulation of waves due to motion is the Doppler effect. Sound waves are useless in space because sound propagates through matter, through air in this example. But in the void of space, sound waves couldn't travel. but we have light instead. That's the basis of the Doppler spectroscopy, detecting and measuring how the motion of a star is affected by the planets, thanks to the variation in light waves. In practice, this is very complex. It requires extremely precise instruments and calculations, and velocity variations down to 3 meters per second from stars that are several light years away, or even thousands or hundreds of light years away, can be detected with modern spectrometers. A spectrometer is an instrument that measures and separates the spectrum of light. And in astronomy, spectrometers can even analyze the chemical composition of faraway stars and planets, thanks to the signature of the elements they are made of. We'll come back to that later. There are such high-precision systems searching for exoplanets thanks to Doppler spectroscopy in Hawaii and in Chile. They are responsible for the discovery of thousands of planets. Apart from the two methods we have discussed, transit photometry and Doppler spectroscopy, there are more methods to discover exoplanets. A visual method, which currently works only for very large planets like those the size of Jupiter with short orbits. It involves detecting how the light reflected by a planet varies. Planets go through phases like the Moon, reflecting more or less light through a cycle, depending on their orbit and how they are positioned. Telescopes cannot distinguish them from their stars, but they can measure how the same cycle of variations in brightness repeats itself and deduce the existence of planets this way. Another method is called pulsar timing. It is limited to planets that orbit pulsars, a type of dead star. We'll talk about the types of stars a little later during our cruise. Pulsars are very dense bodies that rotate and emit radio waves with extreme regularity, making it possible to track the motion, possibly of planets, with extreme precision. Pulsar timing can reveal planets with less than 1/10 the mass of Earth, and can even detect mutual gravitational perturbations between various members of a planetary system, revealing several planets and how they interact at the same time. There are not many planetary systems with a pulsar at their center. They have to be very old systems with an exhausted star that has already collapsed on itself. As you see, these indirect methods are a bit complicated and have a margin of error. But they work and have allowed the discovery of thousands of planets. As of January 2025, there are 5,830 exoplanets that have been confirmed in 4,354 different systems. We are now approaching our first stop, Proxima Centauri b. We are now 4.2 light-years away from Earth, approximately 25 billion miles away. Alpha Centauri is a star system, like the solar system, and the closest to us in the galaxy, but it looks quite different. There is not a single star, but 3 stars. 2 larger and look like smaller versions of the Sun. and one is a smaller star called a red dwarf. In 2016, the discovery of Proxima Centauri b, a rocky planet orbiting the red dwarf star, was unveiled. Interestingly, this planet is in the so-called habitable zone of the star, not too close, not too far, similar to Earth's position in the solar system. Another thing in common between this exoplanet and Earth is the size. Proxima Centauri b may be a bit bigger, at 1.3 times Earth's mass, but the kind of gravity at its surface is probably acceptable for most terrestrial life forms, including humans. But this doesn't mean the planet is another Earth, but it's likely to be habitable. We don't know exactly what it's made of. It could be rocky like Earth, or it could have an icy composition like Neptune, with a thick layer of hydrogen on its surface. The star, Proxima Centauri, is the closest to the Sun, but it is not visible to the naked eye from Earth. Unlike stars that are farther away, because red dwarfs do not emit as much light as Sun-like stars. One challenge for the possibility of life as we know it on Proxima Centauri b is that the star is a flare star. Occasionally, it undergoes dramatic increases in brightness and emissions of all sorts. When these stellar storms happen, it is estimated that the surface of the planet is intensely irradiated to levels of UV rays that would easily kill the most resistant microorganisms on Earth. Proxima Centauri b is hit by intense stellar wind too, which would probably carry away any atmosphere, unless the planet has a powerful magnetic field like Earth that would shield it from stellar wind. What is stellar wind? You know that stars emit light and heat and other radiation, but they also release matter, such as gases or particles, including free electrons and atomic nuclei. The Sun does it too, but on Earth, we are protected from this stream of particles by the Earth's magnetic field, which deviates solar wind. In case of Proxima Centauri b, it is uncertain whether there is a magnetic field, and the stellar wind is up to 2,000 times more powerful than on Earth, making an atmosphere made of gas unlikely. In this case, life forms would have to exist underground, or they would have to be life forms we have a hard time imagining. Yet it is not completely impossible, because the planet is in the habitable zone. So, what is this concept of habitable zone? It is quite simple. Biologists have observed that life forms we know of on our planet need liquid water to appear and survive. It doesn't mean life is impossible without it, but Earth-like life based on the chemistry of carbon, oxygen, and hydrogen probably needs liquid water. The liquid state for water requires quite specific conditions of temperature and pressure. Outside of these, water is either solid or gas. And Earth-like life, especially surface life, would be impossible. When a planet is too close to its star, the heat is too much, and stellar winds are likely to prevent a thick enough atmosphere from existing. With high temperatures and a very thin atmosphere, which means low pressure, liquid water cannot exist at the surface. But if a planet is too far from the star, it doesn't receive enough energy from it, and water turns to eternal ice. Of course, even outside the habitable zone around a star, life could theoretically appear in underground oceans, for example, but surface life, probably not. Now, it's not because a planet is in the habitable zone that it is likely to harbor life. There are many more conditions of composition, temperature, pressure, and maybe a series of coincidences that make life possible. In the solar system, Venus and Mars are also in the habitable zone, yet no sign of life has been detected there. Though Proxima Centauri b is in the habitable zone, its size is relatively similar. A bit bigger, but its habitability remains very uncertain because of stellar radiation and brutal variations in energy its star sends. We don't know whether or not the planet is shielded from this, but there is a slim chance that liquid water exists if the planet constantly presents the same face to its star, like the moon does to Earth. When a body orbits another one and at the same time revolves slowly on its axis so that it always presents the same side, it is said to be tidally locked. The moon is tidally locked to Earth. If this is the case for Proxima Centauri b to its star, there must be a hotter side that receives radiation and a colder, dark side opposite the star. But in between, there could be a thin border region where the transition between extremes happens. Or if Proxima Centauri b has a magnetic field and is rocky, an atmosphere made possible by the magnetic field and maybe a regulation of its temperature by atmosphere, then the sunny face would have liquid water. There are many conditions necessary and a high probability that the planet is just a dead rock, or maybe not even a rock. But we cannot exclude the possibility of life only 4.2 light years away from Earth. But let's escape Proxima Centauri b and resume our journey. We are now going to accelerate even more than last time, because our next destination is OTS 44, 550 light years away. OTS 44 is a planet so large that it could border on a star. It has more than 10 times the mass of Jupiter and is located in the constellation Chameleon. As we resume our journey, and because this planet is going to be very different, let's take a look at the various types of planets and stars that we know of in the universe, or that could theoretically exist. What is a planet, actually? The most commonly accepted definition is that a planet is an astronomical body orbiting a star, massive enough to be rounded by its own gravity, and which has cleared its neighboring region of other bodies by absorbing them or turning them into satellites. However, it's not massive enough for thermonuclear fusion to occur. According to this definition, planets are defined mainly by their size, with both a lower and an upper limit to what constitutes a planet. This definition disqualifies a few bodies that are big enough to be rounded by their gravity, like Pluto, for example, but not big enough to have absorbed planetesimals, protoplanets, around them. This definition of what a planet is remains a bit controversial because it excludes objects of planetary mass based on what or where they orbit. There are satellites in the solar system that are bigger than planets, but they are not considered planets because they orbit another planet before orbiting the Sun. If the criteria of cleaning space was lifted, then Pluto would be classified as a planet again. But so would various bodies from the asteroid belt, like Ceres or Pallas. These are just conventions anyway. But whatever its definition, the term planet also hides a variety of bodies that can be completely different in their size and composition. What planets are made of? In the solar system, there are rocky planets. They have a hard surface and are mainly made of metal and rock. They also have an atmosphere made of gas. But the separation between the atmosphere and the surface is very clear. There are also planets called gas planets like Jupiter or Saturn. They're bigger and don't have a well-defined surface because they are a giant ball of gas, mainly hydrogen and helium. They can also be very dense. Actually, their cores are denser than rocky planets in the solar system because of their size, which compresses the core. Bedrocks are marginal on these planets, and they lack a hard, solid surface. Their density just increases progressively as you travel from the periphery to the core. There are other giant planets like Uranus and Neptune called ice giants. The structure looks the same as gas giants, but their composition is different. Instead of hydrogen and helium, they are made of heavier substances like methane, ammonia, water. We talked about this in previous stories already. But in astronomy, ice is not always water ice. It can also be other compounds like water, carbon dioxide, hydrocarbons. Ices in an ice giant do not form a solid icy ball like an ice planet. They float. So there is no solid surface either. But nothing says all kinds of planets are represented in the solar system. There are other types of planets, or theoretical types of planets, that have not been discovered yet, but could exist. For example, gas dwarf planets, or mini Neptunes. These are planets with a rocky core and a thick envelope of gas or volatile ices, like a crossover between Earth and Jupiter. Planets are called dwarfs when their total size, their radius, is up to 3.9 times that of Earth. Above this limit, they become giants. It is theoretical, but another kind of large gas planet could be made mainly of helium instead of hydrogen plus helium. If a small star loses enough mass, is downgraded to a planet, these would be expected to resemble a gas giant, but they would differ from them by their composition and formation history. Another theoretical type of planet could be ice planets. There are bodies in the solar system with a solid icy surface, like the moons Enceladus orbiting Saturn, Europa orbiting Jupiter, or Triton near Neptune. An ice planet would be a bigger version of these, big enough and independent enough to fall into the definition of a planet. None have been found yet, but there could be iron planets too. Rocky planets generally have a metallic core. When they form, heavier elements like iron tend to migrate towards the core, and lighter elements like silicate rocks stay closer to the surface. But a planet that would form mainly from iron, or that would lose its rocky mantle due to giant impacts, could become an iron planet. The closest planet to this model in the solar system is Mercury, the first planet from the Sun. In proportion, it contains a lot of iron. All these existing or theoretical planets are not random inventions. Their proven possible existence is a result of the planet formation process when a new planetary system appears. You know that according to the current state of theories about planetary system formation, or single star systems at least, it all begins with a large disk of matter, gas and dust, that progressively accretes due to gravitation. Most of the matter ends up creating the star, something to the magnitude of 99% of the matter available. Planets form with what is left of it on different orbits around the star. The remaining matter forms rocks that collide for millions of years, absorbing each other and giving birth to protoplanets that clean up their orbit or become satellites, smaller bodies. If we take the example of iron planets, they are expected to form near a star because presumably this is where protoplanetary disks consist of a lot of iron-rich material. Why iron and not another metal? It is because iron is a rather abundant element in the universe, the sixth most abundant. By mass, one element you are most likely to find in the universe, and by far, is hydrogen, the simplest kind of atom. It is followed by helium. When hydrogen nuclei merge in stars during thermonuclear fusion, it produces helium. So it is another abundant element that stars keep producing all the time. In third place, there is oxygen, followed by carbon and neon. We rarely hear about neon because it is quite rare on Earth. There are traces of it in the atmosphere, where it is a gas, and there is even less in the Earth's crust. There is little neon on rocky planets because it is highly volatile and does not form compounds that could freeze it to solids like oxygen does. So it tends to escape from planets in the early stages of their formation. It doesn't stay trapped in the condensing clouds of gas and dust that form solid planets like Earth. But it is a more significant component of the larger gas planets and stars. In sixth position comes iron, far above any other metal. This is a typology of planets by composition. But there are other ways of categorizing planets, for example by mass. The term super-Earth has become to name a type of exoplanet that is more massive than Earth, but still less than the giants of the solar system. Theoretically, A rocky super-Earth could be habitable, but gravity could be much higher than we are used to. Another concept based on mass is super-Jupiter, a planet that is more massive than Jupiter. Various of them have been discovered, including OTS 44, which we are on our way to visit. Yet another way to categorize planet is by their orbit. This is where the concept of hot Jupiter or hot Neptune appears. These would be gas giants or ice giants orbiting much closer to their star than they do in the solar system. And they are called hot because the proximity to their sun would mean high temperatures in their more superficial layers. As I mentioned before, the main difference between a planet and a star is based on mass. Stars are big enough to ignite thermonuclear fusion and become bigger energy producers in the form of heat, light, and other radiation. It also means there are bodies that are just under or above this limit, very big planets or very small stars. OTS 44, which we are now reaching, is one such body. It was discovered in 1998. It is not a planet attached to a star, but rather a free-floating object that has 11 times the mass of Jupiter, but only 1.1% of the mass of the Sun. We don't know exactly what it looks like, but it is believed to have a disk of particles of rock and dust about 10 times the mass of Earth. This disk could be in the process of accretion, creating a mini planetary system with a very small star at the center and one or several planets orbiting around it. It seems OTS 44 is just at the limit of planet and star, and this kind of object is called a brown dwarf. A brown dwarf is not massive enough to fuse ordinary hydrogen in its core, but it can fuse deuterium. Deuterium is an isotope of hydrogen. What is it about? Elements are defined by the structure of atoms. Common hydrogen, for example, has two particles, one proton in its nucleus and one electron. Any atom with these two particles is hydrogen. The nuclei of atoms may also contain neutrons, another type of particle, and the number of neutrons can vary. These different versions of the same atom are called isotopes. When a hydrogen atom also has one neutron in its nucleus, it is still hydrogen, but its properties are slightly different, beginning with the mass, which is a bit higher. And this particular isotope is called deuterium. Maybe you've heard of something called heavy water. This has to do with deuterium. A molecule of water is made of two atoms of hydrogen and one of oxygen. Most of the time, hydrogen has no neutron. Regular water on Earth is made of that type of hydrogen. But if the hydrogen atoms that combine with oxygen are the deuterium isotope with an additional neutron each, the water it creates has different properties. It is a bit more massive, hence the name heavy water. It freezes at a higher temperature, close to 4 degrees Celsius instead of 0. One of the applications of heavy water is in the nuclear industry, and many nuclear reactors water is used as the moderator, that is to say, the substance that slows down neutrons to facilitate their capture by a fissile material, so that nuclear fuel will become unstable and fission. An advantage of heavy water over regular or light water is that heavy water has a lower propensity to capture neutrons. It's logical because deuterium already has a neutron, so it facilitates reactivity inside the reactor. The nuclear fuel may be less enriched in fissile material. Returning to brown dwarfs. These are bodies that are massive enough to fuse deuterium, because this requires less extreme conditions than ordinary hydrogen. Deuterium fusion gives helium-3, a deuterium nucleus combined with a second proton, so it is no longer hydrogen. It is now helium, with an isotope of helium with the neutron from deuterium. That's why it's called helium-3, because of the particles in its nucleus, 2 protons and 1 neutron. Brown dwarfs emit a bit of light, nothing compared with larger stars, and this is why they are called brown. They are hard to detect by visual observation because of their low brightness, but in fact, to the human eye, they would probably appear magenta or orange-red rather than brown. Even more than with planets, there is a diversity of stars based on their mass or the stage they are at in their life cycle, which determines their kind of luminosity, size, and radiation. Currently, stars are generally classified under a system called Morgan-Keenan, with a letter and a digit indicating their temperature and luminosity. As stars appear and burn for millions or billions of years through the main stages of their lives and then die, their classification evolves. So let's take a look at some types of stars or stages in their existence. As we already started with brown dwarfs, there are at the lower limit of what a star is. You remember when we visited Alpha Centauri, we talked about the red dwarf around which Alpha Centauri b orbits. Red dwarfs are bigger than brown dwarfs, and they are true stars because they fuse ordinary hydrogen. However, their limited mass makes the fusion reaction relatively slow, so they are small-sized stars. Their surface is colder than others, and it is also believed that they can live much longer than bigger stars. Above this category in mass are stars like the Sun, which are sometimes called yellow dwarfs, but their precise classification is G-type main sequence stars. Their typology is based on their luminosity and radiation, but we can just retain the idea that they are rather similar to the Sun. These stars typically exist for around 10 billion years, way less than red dwarfs, because they burn their reserves faster. At the end of their life, when their hydrogen reserves in the core become exhausted, they grow dramatically in size and become so-called red giants. It happens because after billions of years of existence, their core has become rich in helium, the main product of hydrogen fusion. So they begin to consume hydrogen from their more superficial layers, which expands them dramatically. At the same time, the helium core tends to contract, which liberates gravitational energy. As a result of these two factors, the star may expand up to 1,000 times its previous size. When this happens to the Sun in several billion years, it should expand enough to absorb Mercury, then Venus, then Earth, and even Mars. At the same time, the surface temperature decreases, and this is why they are called red giants. Their luminosity tends to decrease. After this phase, it is believed that a red giant collapses on itself, abandoning a lot of its matter that keeps floating in space. These clouds of gas and dust are nebulas that may later participate in the formation of a new system. In the last stages of its life, now that hydrogen to fuse has become scarce in its core, a star of that kind begins to fuse heavier elements, beginning with helium. This is how new elements can be created from the most common ones, like carbon or iron, to the biggest, most massive atoms. But the remains of the star keep agonizing for a very long time, several billion years more, as a smaller body the size of a planet called a white dwarf. Bigger stars than the Sun also exist. They tend to have a shorter lifespan because they burn their fuel faster. When they approach the end of their life and begin burning helium, these massive stars become very bright and are called blue giants. Blue giants are fairly rare because they don't exist for a long time. Still, it can be millions of years. But this is not that much on an astronomical scale. Later, they go through the same expansion process as Sun-like stars and become red supergiants. You have probably heard of supernovas. A supernova is a phenomenon that may happen when a large star reaches the end of its life, either because it has turned into a white dwarf that explodes, or because a star that still has nuclear reactions implodes, suddenly collapses on itself. When this happens, the collapse of its core dislocates its external layers. At the scale of a galaxy, supernovas are relatively rare, but there are so many galaxies in the universe that it is estimated a supernova takes place somewhere every 2 or 3 seconds in the universe. But in the Milky Way alone, there would be 1 to 3 supernovas per century only. The supernova is such a powerful phenomenon. It releases so much energy in a few milliseconds that the dying star can suddenly become more bright than an entire galaxy. And they are important events in the universe too, because they disseminate the elements synthesized by the star during its life. And they create shock waves in space. It is believed that these shock waves are responsible for the formation of new systems. They will transmit motion to a nebula and facilitate the concentration of clouds of floating matter. This matter can then start to spin and accelerate due to gravitation and form a new planetary disk with a star at the center. White dwarfs, these dead bodies of stars, are very dense, and if the star was big enough, they may shrink even more and turn into neutron stars. Neutron stars are dark, small, but extremely dense balls of matter in which the forces at play are so strong that atoms shrink. and electrons and protons combine to form neutrons. The neutron star is made of atomic nuclei. The next stage, if the star was even bigger, may be the transformation into a black hole. Earlier, I mentioned pulsars that emit very stable signals. It is believed that these stars are heavy white dwarfs, or neutron stars, the remnants of a large dead star that rotates fast on itself. So let's return to exoplanets now that we have seen OTS 44, because we have one last stop to make before returning to Earth. We're going to visit one of the most Earth-like exoplanets identified, Kepler 438b. It was discovered using the transit method and confirmed in 2015. You remember the transit method is the measurement of how the crossing of a planet in front of its star dims the light. Its star is called Kepler 438, and it is a red dwarf located 640 light-years away from Earth. Kepler 438b checks a lot of boxes in comparison with Earth. It is in the habitable zone of its system, this region at the periphery of the star that is not too hot nor too cold. It is likely to be rocky and has almost the same size as Earth. Its radius is only 12% bigger. Its equilibrium temperature, that is to say, the theoretical temperature it could have given the stellar radiation it receives, would be around 3 degrees Celsius, 37 degrees Fahrenheit. The main concern we saw earlier with Alpha Centauri b is that it may receive large amounts of radiation from its parent star, which produces regular bursts of radiation. We saw earlier that liquid water was seen as a likely necessary condition for the appearance of Earth-like life. But to search for an environment that could harbor life is just one aspect of a larger field of study called astrobiology, the study of life in the universe. How it may appear, travel through space eventually. What forms, what organisms can be called life? What life forms from other worlds may look like? This is a vast field of study, but one that is a bit paradoxical too, because it studies something we have no trace of at this point. Given that there is no organism to actually investigate, astrobiology focuses on the origins and evolution of life, the kinds of biospheres that could support it, whether extraterrestrial life exists, and how it could be detected. So it touches on many different fields: biology, biochemistry, astronomy, geology, and physics. And it concerns itself mainly with hypotheses that would be coherent with existing scientific theories. We talked about earlier that the search for life focused on carbon-based chemistry. This may sound a bit random or restrictive, as if we lacked imagination, but maybe not so much when we start defining what a living organism may be. It needs to interact with its environment, to find energy somewhere, to build itself. Carbon is a very particular element compared with others because its capacity to be part of many different molecules is unmatched by any other element. It is rather abundant too, the fourth most abundant element in the universe after hydrogen, helium, and oxygen. The energy required for it to make bonds with other elements to form molecules is just at the right level. The molecules formed are stable, but at the same time, they can react when put into contact with other elements. And that's a unique property, and probably the reason why all forms of life we know of on Earth use carbon. To understand how carbon chemistry is crucial, think about the cycle of eating, digesting, and breathing that keeps human beings alive. A large part of what we eat is carbon. It is a key component of not only carbohydrates, but also lipids, proteins, fibers, vitamins. When we digest these nutrients, we take bricks from them to maintain or build our organisms, and we also get energy from the breaking of carbon-based molecules. A part of the carbon is ejected through breathing. We take in oxygen and we take out oxygen and carbon dioxide. All of these transfers of matter and energy are only possible because of the particular properties of carbon. The thing is, no other element seems to be able to replace it. As far as we know, matter in the universe is not different on Earth. 1 light year away or 1,000 light years away from our home, the constraints are the same. And assuming life requires complex chains of molecules that can be broken and rearranged to transfer matter and energy, we see no other element than carbon that could be at the center of it. This is why the search for extraterrestrial life focuses so much on the chemistry of carbon and the conditions needed for it to become the basic building block of life forms. It is not a random option, and it actually looks like a well-informed guess to narrow the search for extraterrestrial life. Carbon and liquid water, which is another ingredient required for carbon-based chemistry to fulfill its potential. Another way to narrow the search when it comes to exoplanets is the type of stars. Sun-like stars are preferred because larger stars tend to have a shorter lifespan, giving life less time to appear before they die. Smaller stars, like the small red dwarfs, may not send out enough energy. But on the other hand, red dwarfs may not be such a bad environment because they exist for hundreds of billions of years, which gives a lot of time to life. A thick atmosphere that would heat the planet through the greenhouse effect could allow the temperature to be sufficient, even with not such a powerful star. There is a hypothesis called panspermia, according to which life could exist throughout the universe, and that it could travel and be distributed by asteroids or space dust. It is possible that the chemistry leading to life with complex molecules may have appeared quite quickly in the history of the universe, maybe after a few million years only. We think the universe is 13.8 billion years old. The basic blocks of life may have formed spontaneously in nebulas or in the first planetary systems. They were made of elements that are relatively abundant, so these building blocks of life may have been distributed to planets as they formed, waiting for favorable environments to combine further. It is impossible to make rules because Earth is the only example we have, and it is true that life on Earth appeared relatively quickly in its earliest forms when Earth cooled down and had liquid water. Earth has supported life for billions of years already. Another aspect of panspermia is the possibility that microorganisms can survive the effects of space, the void, the intense cold or heat, the radiation. These are extremophiles. Organisms on Earth that are able to survive in conditions that would kill most others, like hundreds of degrees or staying frozen for years. Maybe these organisms could be ejected with other debris when a planet collides with an asteroid and stay dormant for years or even centuries until they randomly land on another planet, where they will become active again and colonize a new environment. These are just hypotheses that sort of fit with scientific theories. They are not absurd, but there is no hard evidence that this ever took place. Is there life on Kepler 438b? We don't know. It is so far away at 640 light years. It is hard to imagine human beings ever going to check. It sounds absolutely improbable. But the idea of flying to Mars would have sounded equally absurd 3 centuries ago. We are now maybe just a few years from achieving that. So perhaps our children will find a way that we cannot even start to think of now to travel faster than light and reach these faraway worlds. For now, our journey is nearing its end. We are now going to return to Earth even faster than we left. You can now stop focusing and start to dream of all the stars, comets, and clouds that we are crossing on our way back to Earth. I hope you enjoyed our adventure, and I invite you to discover and learn more. Now you can let go and sleep. Or, if you are not sleepy yet, you may pick another story from my ever-growing library. And until we meet again, good night. Sleep well.